This is Yingfei Gu, member of the Institute for Advanced Study at Tsinghua University. Today, we are very happy to have Alexei Kitaev with us. Alexei, thank you for joining me.
Thank you.
It's great to see you here in China, and congratulations on your award.
Thank you.
Can you give a self-introduction to those people who are not super familiar with you and your work?
I'm a theoretical physicist, and I solve various problems in theoretical physics. My first successful work with my fellow students, we all worked at the Landa Institute as students, Leonid Levetov and Pavel Kalugin. This work was on quasicrystals, and later I studied quantum computation, some quantum algorithms and quantum error correcting codes. And inspired by the problem of protecting quantum information, I started working on topological quantum phases. Topological quantum phases are certain phases of matter that occur at low temperature in some special cases of interacting spins or electrons. And those phases have a nice feature that they can store quantum information and protect it from errors. And the error protection was my original motivation. It's due to my work in quantum computation, and then I continued studying those topological phases on their own. And in the process, I invented several models, like the toric code, the surface code model. This is one example. The Majorana chain, the honeycomb model. Later, I got interested in quantum chaos and its connection to black holes. And that question was addressed using the so-called Kitaev model. Sajdev previously formulated a model which was rather complex, but it had the right properties to demonstrate this connection between black hole and quantum chaos. I anticipated it would be true, but I didn't know for sure. And the first thing I did is to simplify the model so that to make it easier to solve. These are the main areas I have worked on. Currently, I'm working on topological quantum phases again, but I'm studying their mathematical properties, and right now I'm focusing on a question that may sound boring, maybe it is boring, but it's somehow necessary to make progress. How does one define a topological state mathematically? I hope that this will help clarify some subtleties that people try to ignore, but they may indeed be just technical subtleties, or they may be some deep problems that need to be addressed.
Your ability in inventing toy models to capture the essence of the physical system is remarkable, and is probably incomparable. Like, how do you come into this style? Like, what develops this style?
Very early on in my career, I realized that I like such models, and I took inspiration from the work of Anderson, who invented a model of spin impurity. At that time, I was studying applied mathematics. I started my undergraduate studies in applied mathematics, but I came across this paper by Anderson, and it fascinated me. convinced me that condensed matter physics is an exciting subject.
Oh, great. So is that a model about the Kondo problem? Or?
No, it was about a more basic thing with the impurity. The impurity will have a spin, a localized spin, or whether the spin will be dissolved. And the model involves coupling, like hopping between localized states and free states, as well as interaction.
Ah, I see. Yeah, but your special ability is to make the model solvable. Like, is that what you considered in the beginning, or are you just trying to cook up some interesting model?
I tried to cook up some interesting models that would capture one thing at a time, basically. I tried to remove unnecessary complexity and construct a model that would have some interesting properties, but getting rid of unnecessary details makes it easy to study the model.
I see. So, yeah, sometimes when we study your model, it's kind of always come together with a comprehensive theory. When you invent this model, do you have the idea of this theory before you construct a model, or you actually realize or study the theory when find the theory when you carefully study your own model?
Usually, when you construct a model, you have some idea what phenomenon you want to capture, so you already have some theory. But when you write down the model and try to solve it, you discover new things, and that's basically the goal of constructing the model.
So let's elaborate more on this. For example, for the Toricode case. So what was your original motivation, and what you discovered, something unexpected?
The Toricode was a quantum code, and the motivation was to protect quantum information, to construct a quantum code that would tolerate a large number of errors, a large error rate that could be scaled up. And I knew about the fractional quantum Hall effect. I read some papers that made a statement that the ground state on the torus in the fractional quantum Hall effect is degenerate.
When was that? Why?
This degeneracy was discovered in 1980s. I don't remember exactly when, and I studied quantum Hall effect as a graduate student, so I knew about the quantum Hall effect. Maybe not this particular fact, but about the subject in general. And I realized that degeneracy is something like a quantum code, and the new ingredient was to realize that it is indeed a quantum code. It is stable to perturbations. And of course, another aspect is to simplify things. The Toricode model is pretty simple.
Right. Yeah, so it's takes several years from you first read the fractional quantum Hall, and then you work on this quantum code stuff.
Right.
Yeah, but this experience helps you, or something you studied reminds you or help you to
Yes.
I see. And so after you write down your Toricode, and so what kind of new things or the biggest surprise after you have this model and study it?
A surprise? I'm not sure about big surprises, but after writing down the model, I studied perturbations to the model, and one work on perturbations, the main result was actually not very new. It was the same model in a different formulation was previously studied by Frotkin and Schenker. Actually, it was many years before. But they considered it as a field theory model or a statistical mechanics model rather than a quantum Hamiltonian. And I realized that these two models are connected, and collaborating with other people, we did some numerical study on the stability of that model, and we discovered that besides expected features, there is some unexpected feature. It's not related to the properties I was originally interested in, not related to quantum error correction. It was a work with Stemp, Tupitsin, and Prokofiev.
I see. So then let's talk about your honeycomb model, which has a pretty long appendices. And each appendices now turns out to be very important and sometimes become a subfield its own. So like, so how did you, having so many ideas or mathematical structures, like affiliate to the single model? What kind of the ingredients that you have in your mind to make all these things integrated in the single model?
The model contains anyons.
Right.
And one of the appendices is about anyons. I did not invent the theory of anyons. It was invented before by many smart physicists and mathematicians. I mean, different aspects of the theory were invented by different people, including Edward Witten. He found a relation between Chern-Simons theory and Jones polynomial. But I took a mathematical formulation based on modular tensor categories, fusion rules, braiding rules, and just wrote up the properties carefully such that they're accessible to condensed matter physicists. And these properties are actually used to study the model. I didn't know that the model would have this particular type of anyons. I had to solve some equations, and this appendix contains the equations. But other appendices are slightly different. Probably there is more original work put in those appendices, in particular the formulation of the chiral central charge in terms of correlation functions. Was original.
So what about the SYK model? Like, tell us some story about how you invented this model and what was the original purpose and what you found unexpected.
The original purpose was to understand what happens near the black hole horizon.
But why this problem draw your attention in the first place? You previously only worked, as far as I know, for in condensed matter and quantum information. Like, what caught your attention? Gravity.
It's an exciting problem by itself. This is the main motivation. A secondary motivation was that there was a lot of talk about holography and its connection to condensed matter phenomena, and it sounded suspicious to me. I was trying to understand what it means.
So you want to find some concrete, explicit model to.
Right.
I see.
And in the end, it was very good that the SYK model has some elements of holography, but it wasn't fully holographic, not the same type of holography that is found in supersymmetric models.
So, you invent this model, and it certainly help you to clarify some question. What found most unexpected part of the SYK model after you studied? What was the part that is not foreseen before?
Oh, okay. Let me start with what I did expect. I expected the out-of-time order correlator to grow with the exponent that is the same as in black hole. It's called maximal chaos. And this happened to be true, and I was very lucky that it is true. But the details were not anticipated. One thing is the invariance under diffeomorphisms. The Schwinger-Dyson equations in that model are invariant under diffeomorphisms of a circle if we take the low temperature limit. And related to that, there is the Schwarzschild action. So these two things were unexpected, and I wouldn't have come up with those ideas had I not studied this model in detail.
I see. Great. Yeah, so I realize like many of your work has like a deep association with mathematics, and somehow we have seen so many great Russian mathematics and physicists. Do you think there's some certain unique elements in Soviet Union's education system that cultivate so many talents?
Let me mention one very important element, and this is high school education. There is a system of, at least there was a system, and I hope parts of it still exist, of mathematical schools. There were a few very elite schools in Moscow and perhaps in other places too, but there were also sufficiently many schools where talented students would come to study for the last 2 years. Like in our city, I grew up in Voronezh. It's a city, now it's more than 1 million people, but it was less than that in my time, and there were 2 such schools in the city. And people would come to this more advanced mathematical classes from the same school or other schools in the city, and even from small towns around.
So that's so you need to apply for that, or
yeah, you needed to apply, and there was an interview. They would select capable students.
I see. So it's only for mathematics, or they have many other different?
It was more mathematics than in regular high school, and a little more physics.
Little more physics.
Yeah.
So mainly mathematics.
Yeah.
Yeah. But when you go to university, at some point you choose to work, put your time into physics. So
yes.
What drives you, or what? Yeah. Why physics is your like attract you?
I was and am interested in both physics and mathematics. There were several factors that affected my choice, and one of them is I participated in physics Olympiads in high school, and I won some prizes on those Olympiads within the Soviet Union. And for math Olympiads, I didn't really try, but I would try to solve math problems from the International Olympiad. I would solve maybe 1/3 of those problems. So I felt that I'm stronger in physics than in mathematics.
I see. Okay, so yeah, at that point you have decided like to study physics in university, and
yeah, can mention one special program that we had in our university, Moscow Institute of Physics and Technology. It was a theory group. There were actually two theory groups where there was an additional entrance exam. And I switched from applied math to physics, in particular theoretical physics, by passing that exam. Actually, there were two ways to pass the exam. The other way was to do the Landau theoretical minimum, which I couldn't do. But I just passed the exam for the theory group.
Yeah, so you worked in Landau Institute for several years and then moved to US. How do you compare your working experience, your early career in Russia and those later times in US? So environment, interactions, all kinds of things.
First, I came to the Landau Institute as a student, and it was around 1984, I think. Mid-80s, and that was a great time. There were many bright theoretical physicists working in various areas. If you had a question in theoretical physics, you could find the right person to ask that question to. And it was very exciting. But later on, the system fell apart when the Soviet Union fell apart. The economy became bad, and most people left.
See, so yeah, so.
And I stayed in Russia for a few years. Actually, during those years, I earned additional money by visiting places abroad, like the Weizmann Institute. This was a hard time economically for Russia, and for scientists it was quite hard. So, but I was lucky that I could got those temporary positions and earn some money. But I didn't want to leave. I hoped that thing would become better, but they didn't. And eventually I realized that it's better for my career to work in a different country.
So yeah, that's the part about like your uniqueness in physics and style and your experience. Now I want to shift to the talk about your cross-disciplinary style, like aspects of your research. So you have been contributing to both condensed matter and quantum information. Now these two fields benefits a lot from cross-fertilizing. And I want to ask, in your own experience, how does it work? Like has your background in condensed matter physics influenced your early career working in quantum information, quantum computing, and how your early career about this quantum information influenced your later works, which could be purely condensed matter or something related to gravity as well?
Right. I mentioned the connection between the toric code and fractional quantum Hall effect.
This is example.
One example where I learned something in condensed matter and applied it in quantum information.
Right.
And the other way around is the realization that system can have error correcting properties. They can be stable to perturbations. And I mentioned anyons.
Right.
In particular, non-abelian anyons. With non-abelian anyons, one can have degeneracy with two or more anyons. This degeneracy is related to the fusion channel. And that had been known before my work in anyons, but somehow people didn't realize that it's a quantum code. The system has error correcting properties.
I see. So kind of the experience in one side, like give you more give you kind of broader perspective and some kind of new motivation for a particular solution.
Exactly.
Mm-hmm. Okay, when you were working on this quantum information business, the field merely starts. Like, what draws your attention in the beginning, and what kind of work triggers you to let you to put your energy into this field?
I would say the field hadn't started. It was just the right time for this field. But I learned about the idea of quantum computation as an undergraduate student by reading the book by Yuri Manin, Computable and Uncomputable. Mm-hmm. It's a book about mathematical logic. Mm-hmm. But in the introduction, he mentioned a few examples where logic might be connected to the real world, and one example was quantum mechanics. Mm-hmm. And the idea that was expressed just in 2 paragraphs was that quantum mechanics are computationally complex, and it might lead to new models of computation. Mm-hmm. Mm-hmm. And that was very exciting. I knew there was such an exciting problem, but I couldn't make progress until I learned about further developments. In particular, I read Feynman's papers on quantum computing. Mm-hmm. One paper was in 1982, I think, and the other in 1985, though I might misremember the exact years.
I think I remember Feynman gave the talk in 1981, and the paper comes out the next year, I guess.
Maybe it was in 1981. Mm-hmm. But after reading those papers, that was not enough for me to start. But when I learned the mathematical model mm-hmm. of quantum computation, mm-hmm. Then I started to work in that area, because mm-hmm. It was possible to make progress based on this exact formulation of the problem. Mm-hmm. Previously, it was a bit too vague formulation.
So you start to work on this like during your graduate school, or after graduate?
No, it was after graduate school.
Mm-hmm. See. So like, for example, for the more specific work, for example, when you define QMA, or later you find some quantum phase estimation. Mm-hmm. So are you triggered by some developments in the field, or you just work on your own and find the natural motivation to do all these things?
The phase estimation algorithm was my way to solve the discrete logarithm problem. Mm-hmm. I heard about Shor's result, the solution to the discrete logarithm problem, mm-hmm. and before I could get a hold on a copy of Shor's paper, I just solved this problem, and the solution used the phase estimation algorithm. Mm-hmm. But QMA is based on Feynman's idea, or clock. Mm-hmm. Yeah. I just formalized that idea.
Oh, I see. Mm-hmm. Now, 30 years later, this quantum information, this field has advances a lot, in particular in experimental side. So just imagine you are 30 years younger, like just to start your career. So you have to choose one particular topic's direction in this quantum information field. What kind of topic will you choose? Like, I'm very curious about it.
In quantum information?
Yeah.
I probably wouldn't choose quantum information, but let me explain. In mid-90s, it was a golden time for quantum information. It was really an area of fundamental physics.
Right.
Now it's an applied field.
Yeah.
There are still some interesting questions. In particular, there have been a breakthrough in quantum error correcting codes, so-called low-density parity check codes.
Right, right.
That happened a few years ago.
Right. Mm.
And there might be further breakthroughs, maybe a completely new quantum algorithm will be found in the future. I don't know. But to find a quantum algorithm, I think one has to know both quantum mechanics and quantum computation and some advanced area of mathematics, maybe algebraic geometry or number theory or something like that, to connect these two things.
I see. Yeah, okay. So you have also worked with some, but not many people. For example, they come from different backgrounds. For example, Michael Friedman, mathematician, and John Prisco, physicist, and other postdocs. So what's your style of collaboration, and how do all these collaborators influence your thinking or work?
There are different aspects of collaboration, or just discussing physics and mathematics. The actual work on a paper, or just discussing various problems. And there have been several occasions when I particularly enjoy collaborations, in the sense that my ideas and my collaborators' ideas complemented each other, and this is really fun when they complement each other.
Right.
But there was a different aspect just discussing physics. I learned some ideas in field theory from John Presco and quantum information. And I learned a lot from a lot of mathematics from Michael Friedman. I really enjoyed his explanations of mathematical concepts.
So he's a good teacher, in that sense?
Yeah, I think so.
Yeah, great. So now I want to shift to your first experience in China. We know that this is your very first time coming to China. And how do you feel so far?
I'm very grateful to you and other people who met me and made all arrangements. I understand that it was pretty complicated. I mean, this whole thing is complicated, but I really appreciate your hospitality.
My pleasure. But since now you see China in your own eye, does it meet your imagination or something like that? So do you find something particularly interesting, like you didn't see in other country, or something like that, special about China?
I'm trying to figure it. Feels that kind of people are pretty happy here, which I didn't expect. Yeah, and things seem to work, and I'm trying to figure how they work.
Okay. So regarding the academic aspect, so you have certainly interacted with many Chinese scholars over the past 3 decades, say. So how do you compare the people you encountered, like Chinese scholars in 20, 30 years ago, to the people you encounter today?
Today, students and postdocs who come from China to the US are much better prepared to do physics. And their English is better, and their skills are better. One thing that really frustrated me some 20 years ago, when I talked with Chinese students, they were afraid to discuss physics programs. When you discuss physics programs, you need to sometimes object. You see that the other person is saying something wrong, or maybe you need to say no. If I ask a question, the other person should answer yes or no, and that is actually an important piece of information that I'm really asking for. It's not, but they were afraid to communicate.
Right.
And these days, people are better prepared in this sense.
I see. So in some sense, more relaxed. Right?
Yeah.
Yeah.
Mm-hmm.
Yeah. Now, in the end, getting to the end of this interview, can you say something to those young scientists, young scholars who are reading your paper, studying your work, and just some general advice or encouragement?
I think there is no universal advice, because every person has different strengths. I think it's important to try various things and figure what you're good at and what you're interested in, and just pursue your dream.
See. Yeah, thank you very much for joining the interview, and I hope you have a good time in China.
Thank you.